Okay, in this video we're going to begin chapter 10, which focuses on dienes and allylic resonance. Dienes are compounds that have two alkene groups in them. And what we're going to see in this chapter is that the chemistry can be very different when you have two alkenes than if you have one, depending on the arrangement of those two alkene groups. Okay, I'd like to bring out a few terms from the past that we're going to be using a lot in this chapter. Okay, so this group right here is called a vinyl group. This group here with an extra CH2 separating the double bond from whatever the other part of this molecule is referred to as an allyl group. Okay, so when we have a compound that has a double bond in it and we're looking at the adjacent position, okay, we're going to use these terms that you see in this diagram to describe the position of these groups. Okay, alright, so this is a vinylic carbon. This is an sp2 carbon. The sp3 carbon adjacent to a vinylic carbon is going to be called an allylic carbon. Okay, and this right here beside the double bond is the allylic position. The hydrogens at this position are referred to as allylic hydrogens. The hydrogens at a vinylic position, like this one, are referred to as vinylic hydrogens. Okay, alright, so this is not just going to be about dienes, but it's also going to be about allylic resonance, and we're going to see how dienes are a major precursor to compounds that have allylic resonance. Okay, let's just briefly visit one nomenclature point here. A diene is named pretty much the same way we named alkenes. It's just that we have two alkene groups that we have to name now. We're going to number from the end that gives the lowest number to the first alkene carbon. And we're going to give a number to the first carbon of each alkene group. And the name is going to end in diene. Okay, so in this compound up here, we would number from the left end because C1 would be part of the alkene carbon. If we numbered from the right end, we wouldn't get to our first alkene carbon until C2. Okay, so the carbons that we're going to define as being part of the alkene group, this is going to be the 1 alkene and this is going to be the 5 alkene because that's the first alkene carbon in that chain. Alright, so this compound would be hepta-1,5-diene or 1,5-heptadiene, depending on if you believe in the revision of the IUPAC rules a few years ago. Okay, first we're going to look at things that aren't dienes at all. Sn1 reactions in allylic systems. Okay, so when we do an Sn1 type reaction in an allylic system, what we see is some unusual features. You may recall this reaction right here from chapter 4, right? ROH plus HX going to RX plus water. Okay, so that was a reaction in chapter 4. That was the first mechanism that we really ever discussed in this class. Alright, so the compound on the left is the direct result of that reaction. But the compound on the right seems to have undergone some sort of rearrangement. It's not a skeletal rearrangement because there's really no movement of the carbons. Every carbon is attached to the same carbon in the left structure and the right structure. It's just the degree of attachment. So the location of the double bond is different, but what's attached to what basically remains the same. Okay, let's look at the mechanism for these reactions. Of course, the first thing we want to do here is protonate the alcohol. Alright, so we get the protonated alcohol. We make the carbocation right here. And just like in chapter 4, this carbocation reacts with chloride ion to make the substitution product. Okay? But what we have going on here is a case where our carbocation really isn't what we have pictured there. Because of this adjacent double bond, there's actually a resonance interaction going on right here. Okay? And what we can say here is that we now have a resonance stabilized carbocation. This type of carbocation is specifically known as the allylic carbocation. Alright, so if we now take this alternate resonance structure and react it with a halide ion, of course, halide ion would react right there, and that would produce the other compound. Okay, so if we look at the structure of the allylic carbocation, okay, I actually need to draw this with some stereochemical stuff here. Okay, so here's the double bond right here, and here's the carbocation. All we've done when we interconvert these two structures is we just moved this electron from right here over to here. Okay, so that's the only difference between these two structures right here. It's just the location of this one electron. So recall that resonance structures are defined as you move electrons without moving atoms. So the connectivity is the same in both of those resonance forms. Let me just draw the resonance hybrid. If you recall from the chapter 1, we were drawing resonance hybrids too. Okay. Alright, so there's our resonance hybrid. Alright, now if we look at these two resonance structures, and I ask the class, what's your favorite? Which one do you like better? A lot of the class is going to gravitate toward this one. And what's the reason for that? Of course, it's because it's a tertiary carbocation. But a sizable number of the class might have a preference for this resonance structure, and if you like this one better, of course you could defend yourself also by saying it's the one that has the more substituted double bond in it. Now if you look at the products, this product here of course would be much more stable than this product, because the only real difference here is the degree of substitution at the alkene group. This has a tri-substituted alkene, this only has a mono-substituted alkene. Okay, one other interesting fact here. There's another compound that could give rise to these two products in exactly the same reaction. And that's this one, right? Because this one, if we imagine it going through the same steps, would produce exactly the same set of allylic carbocations. This one would produce this one first, and this would be the resonance structure we write. But we know that we don't really produce a resonance structure first. Resonance means that the true structure is some hybrid of those two structures. Okay. Alright. Below this we have an actual Sn2 reaction, or Sn1 reaction, sorry. And this is a solvolysis reaction. We're heating this compound up in methanol. And what we see here is that we have two products, and they kind of differ like the ones before. They have exactly the same connectivity. It's just the location of the double bond is different. Sorry, they have the same carbon skeleton. It's just that the double bond's different. The oxygen's also in a different position as well. All right, this is an Sn1 reaction, and remember, here's the mechanism for the Sn1 reaction. We dissociate the halide to get a carbocation. Like the one above it, this carbocation here is also allylic, and so we can write this resonance structure right here for it. This is a hybrid. The true carbocation is a hybrid of these two structures right here. Having the methanol attack here is eventually going to give us this product, and if methanol attacks here, we'll eventually get this product over on the right. And we get these two products after we lose the extra hydrogen from what was originally methanol. Okay, so this also involves an allylic carbocation. All right. As before, there is another distinct compound that can give rise to the same set of allylic carbocations, and that's this isomeric bromide right here. Okay, and again, like before, we're going to dissociate the halide. Here we're going to get this one. This is the first one we would draw, but once allylic carbocation is formed, it's a blend of all of its resonance forms, which are these two resonance forms right here. Okay, here's a problem for you. Write a mechanism for the following reaction and give me the structure for another compound that's going to give this identical set of products. Okay, so this mechanism is going to be the same as the other one, right? We're going to start off by protonating the alcohol. Okay, so HI is going to give us the protonated alcohol, and remember that there was this hydrogen here. I want to emphasize this because once we get to this carbocation right here, I always like to say don't draw the bond line diagrams around charged species because it's easy to forget that the hydrogens are there. There's just too much analysis to go through to instantly recall whether there's a hydrogen there or not. All right, so once we have that, okay, it's going to react with I- to produce the first compound, and of course since it's an allylic carbocation, we can't deny that it's going to have a resonance structure that basically swaps the location of the carbocation and double bonds, and this is going to lead to the other product right here. Okay, the second part of this question, what other compound will give rise to these products? It's actually going to be the alcohol that corresponds to that iodide right there. So this alcohol would also give rise to the same set of iodides. Okay. All right, let's look at allylic radicals now. If we attempt to do a free radical halogenation of an allylic system, these reactions tend to be very selective for substituting at the allylic position. Okay? All right. There's not it's a little bit harder to chlorinate than it is to brominate. Chlorine, say 500 degrees, is going to give this as a major product. Bromine and light will give this, and it'll give us quite a bit of this too. This is the not the free radical addition, but the electrophilic addition that you saw in chapter 6 that goes through the bromonium ion. Okay. The deal here is that if you initiate it, the reaction goes by the free radical pathway, and if you keep the concentration of bromine relatively low so that there's more radicals and less Br2 or less bromine, electrophilic bromine sources, you'll get more of the allylic isomer. Okay, Bromine is not the ideal reagent for doing this, however, because of the side reaction. The ideal reagent here is this one. This is one of these abbreviations in organic chemistry that has to stick with us forever. N-bromosuccinimide, NBS. This is the reagent of choice for doing free radical halogenation of an allylic system. Okay? This produces as a byproduct this compound here known as succinimide. Back in the old days, people would do these reactions in carbon tetrachloride. And both NBS and succinimide are white crystalline compounds, but NBS is denser than carbon tetrachloride. Succinimide is lighter than carbon tetrachloride. So you would just notice that the white crystals started floating, and that would tell you that your reaction had succeeded. Okay, so N-bromosuccinimide serves as a source of bromine at low concentration through this reaction right here. If NBS reacts with HBr, it'll make succinimide and bromine. Okay? Alright, so the idea here is as you form HBr, you generate more bromine. So the concentration of Br2 stays low at all times. Okay? It only forms as fast as you make HBr. Let's look at the mechanism for this reaction. First, let's consider the structural issues. If you look at the three different bond types you have in cyclohexene, there's the vinylic CH bond here, which has a bond dissociation energy of 440. The allylic is 368, and the plain old secondary out here is 397. What we see here is that the CH bond that's allylic is the weakest. And remember, we correlated weak bonds with some sort of stabilization of the resulting free radical. So this means that the free radical at the allylic position is more stable than at any other place. Okay, so this means that we have now a resonance stabilized radical right here, like this one. And we can write two different resonance structures. These are degenerate resonance forms. Okay, I'm going to try to draw this free radical here. I'm not sure I drew a great perspective, but what you can see here is really that we have three different electrons, and there's confusion here. How do you know the double bond is here and not here? Okay? Alright, so the allylic free radical, of course, is a true resonance form. Both resonance forms would be contributing almost, in this case, exactly equally to the overall structure. And what we would see here is that we have half a spin at each of the N carbons and no spin in the middle. Okay, so here's our mechanism. Our initiation step is we break the nitrogen-bromine bond. Okay? Alright. So the bromine radical that we generated is now going to pluck off this hydrogen right here, and it's going to make the allylic free radical, and it's going to give HBr as a byproduct. Okay? The HBr that we made as a byproduct is going to make bromine now from this reaction that we showed in the previous slide. Alright, so the bromine we have is going to, the allylic radical is going to abstract a bromine from Br2. This is going to now give us the allylic bromide and Br dot. And this is going to come back in here, recycle itself, and continue the propagation process over and over and over, making lots of the allylic bromide and lots of succinimide. Okay? Alright. So this is the mechanism. Let's look at a few complications that arise from this free radical mechanism. Alright, so let's imagine that if you carbon-13 label one of the vinylic carbons of cyclohexene, you find that your label gets scrambled over 3 carbons. Okay, now let's see if we can rationalize why this is the case. The label, the C13 label, would be here, here, and also to some extent in the middle. Okay, actually probably about a 1-to-1-to-1 ratio of all 3 of these compounds. We're going to see in chapter 13, the spectroscopy chapter, how carbon 13 is a beautiful way to label the system. It's so easy to detect by a technique called NMR spectroscopy. Okay, all right, so what's happening here? In our mechanism, we're pulling off the allylic hydrogen here, and this resonance structure has either the resonance has the radical split between where C13 is and this C12 that we had originally had here, right? So this one will react with bromine to give us this compound. This one will abstract a bromine from the Br2 to make this compound. How did we make the other compound? Well, it turns out that these two sets of allylic hydrogens are not equal now, right? Because one of them is right beside the label and one of them is 2 carbons away from the label. Okay, so if we pluck off one of the top hydrogens, we get this radical right here. And in this one, what we notice here is that the label is in the middle of the allylic system, so both of these resonance structures here are technically equal to each other, and the reaction with bromine puts the bromine at that carbon 12, which is adjacent to the original C13. Okay, let's look at another complication that occurs from this allylic resonance. The reaction can be quite messy if your 2 allylic resonance structures aren't exactly the same compound, or they're not degenerate. Take this example here using 1-pentene. If we treat this compound with NBS and light, we're going to get a mixture of these 2 allylic bromides that you see right here. Okay, how do these arise? Of course, it's due to allylic resonance. Okay, all right, so bromine is going to pluck off the bromine radical that we generated from NBS and light is going to pluck off the allylic hydrogen right here to generate the radical here, and this is going to react with bromine. But we have to consider that there's also a resonance form, which is this compound right here. And this resonance form is technically structurally different from this one. So when we react that one with bromine, it's going to produce the alternate product right here. Okay, so these reactions with unsymmetrical allylic systems can be quite messy. This reaction produces both of these compounds. Okay, so let's look at the effect of allylic resonance on the relative rates of Sn1 and Sn2 processes. Okay, if we had to compare the relative rates of reaction of A going to C versus B going to D, the Sn1 reaction here, which I hope you've realized is ideal Sn1 conditions, involving A is going to proceed a lot faster than the reaction involving B, because the intermediate carbocation is tertiary and allylic. Remember that resonance is stabilizing. Okay, so our allylic carbocations tend to be more stable than tertiary carbocations. So now we have something that's even better than tertiary. All right, so let's think about the mechanism for dehydration and see if we can predict which of the alcohols below are going to react at the fastest rate with sulfuric acid. Okay? And again, try to do this yourself, pause the video, and then restart it. Okay, this relative rate in this case is totally due to the relative stability of the carbocation intermediates that you're going to get. Remember, you're going to protonate the alcohol and lose water and leave behind a carbocation at whatever position the alcohol is attached to. All right, so if we look at the carbocations, sorry, there's I should have animated that one a little, but here we see that reaction A is faster because it involves a tertiary allylic carbocation versus just a simple tertiary. Tertiary allylic is better than tertiary. Okay, so in this last reaction here, we're going to predict that this one right here is going to be our fastest. This is because it leaves behind a carbocation that's both tertiary and allylic. This one here is going to be our second fastest because it's going to leave behind a carbocation that's secondary and allylic. This one is going to leave our third, sorry, this is number 3. This is our third most stable one because it's leaving behind a carbocation that's merely tertiary. Remember, this is not allylic because it has an sp3 carbon separating the carbocation from the alkene. And the slowest one is going to be this last one over here, which is merely secondary, okay? There's no additional stabilization of that carbocation. So that one is going to be the slowest. Okay. All right, so what does this have to do with, sorry, one other issue, and that's that allylic systems also activate the Sn2 reaction as well. What we would find if we compared the relative rates of reactions A and B here, that reaction A is much faster than reaction B. Okay, so allylic halides are activated for the Sn2 reaction relative, sorry, forgot to turn off email, relative to the analogous halides without this allylic activation. Okay, all right, so here we see that our halide in this case is activated. And what's the source of this activation? Well, one is the fact that because this halogen is in the allylic position, this is a weaker bond, so it's easier to break. It's weaker just like the CH bonds in the allylic position were also weaker. There's also, if we remember this pentacoordinate transition state where this is coming in just as this is going away, there's orbital overlap between this p orbital and this adjacent double bond right here. So all of these things tend to accelerate an Sn2 reaction involving an allylic system. Okay, so the compound below has 3 different halogens. See if you can predict the product of this reaction before I actually present the answer. Okay, so in this one we have 3 different halogens. Okay, this is primary and allylic. This is just primary, and this is vinylic. Halogen at sp2 carbon, that type of halogen doesn't do the Sn2 reaction. So we're going to substitute preferentially the allylic chloride. And this is the product we would expect from this Sn2 reaction right here. Okay, finally we're going to get to the real meat of this chapter, and this is dienes. Okay, and I have here 5 compounds: a simple alkene, an alkyne, and 3 different compounds that have 2 alkene groups in them. Okay, all right, so if we look at dienes, we're going to classify them as one of 2 ways. An isolated diene has one or more sp3 carbons separating the alkene units. Okay. In a conjugated diene, we have 4 consecutive sp2 carbons, and in a cumulene, we have 1 carbon, it's sp hybridized, that's part of 2 different alkene groups. Okay, we can compare the stability of the diene systems by just comparing the heats of hydrogenation. Okay, so the simple alkene on the far left has a heat of hydrogenation of 126. It's a monosubstituted alkene. The isolated diene has 2 monosubstituted alkene groups, and the heat of hydrogenation is exactly twice what the compound over to the left is. So there's nothing special about the isolated diene structural feature. It's 2 independent alkene groups. But what we see when we move to the conjugated diene is that there's some significant stabilization. Okay? The heat of hydrogenation for the conjugated diene is substantially lower than it is for the isolated diene. And for the cumulene, we see just the opposite trend. This number here is much higher than this number, so there's destabilization. The cumulene is actually comparable in its stability to the alkyne. Okay? Alright, so conjugated diene, this is the most stable structural arrangement for 2 alkene groups. This is something you need to remember for a long time. Just a simple phrase. Conjugation is good. Okay, on a cumulene, this is the least stable configuration for 2 alkene groups. An alkyne and a cumulene are of comparable stability, or a comparably stable arrangement for 2 pi bonds. Okay, and they both involve 1 or more sp carbons as well. Okay, it's not just alkenes that can be conjugated. As long as we have any set of pi bonds in this alternating arrangement like you see here, we consider it a conjugated system. Okay, so here's a conjugated system here, here's one here. There's lots of conjugation in this molecule. In fact, there's really 4 double bonds in conjugation in this compound here known as styrene. Alright, here we see a carbon-oxygen double bond replaces one of the carbon-carbon double bonds. But remember, that's also a pi bond, so this is conjugated. Here we see a conjugated acetylene or a conjugated enine system here. And in this last case, remember that the cyanide is a carbon-nitrogen triple bond, so this is also a conjugated system. Okay, let's do a problem here. Let's rank the following dienes in order of their relative stability. Place a number 1 underneath the most stable one and a number 5 underneath the least stable one. Number 1 concern is conjugated versus isolated versus cumulene. Number 2 is the degree of alkyl substitution. Notice that this benzene ring is common to every one of these. Okay, so we can't really, this is really conjugated, but it's the same degree of conjugation in all of the systems, so we can't use that all by itself to separate or to rank the relative stability of these compounds, but we can rank them as to regard whether they're conjugated to the benzene ring or not. Alright, So let's look at and classify them as to their conjugated, isolated, or accumulating. Okay? All right, so sorry about that. I just wanted to see what was on the next slide. So that's the answers on the next slide. This is completely isolated as far as the dying part goes, right? These double bonds are not conjugated to each other, and they're not conjugated to the benzene ring. There's an sp2 carbon separating them there. There's another sp3 carbon separating them there, sp3 here, and an sp3 carbon there. So this has no conjugated double bonds. This one has a conjugated system with a double bond right there, right? So this double bond is conjugated to the benzene ring. This one is isolated. So this one has a conjugated and an isolated. This one has the whole system conjugated, okay? All right. This one down here also has some degree of conjugation for one of the alkene groups, but this one is isolated, just like this one is. And this, of course, is accumulating. And this little dot here represents a carbon in accumulating. Sometimes if you draw them, it looks like a continual line, or it just looks like a really, really long CC double bond. So you have to put that dot in there to let the person know that there's a carbon right there. Okay, so we ought to be able to rank. This one right here is our most stable. This one right here is our least stable. This one is kind of our second least stable, and we have a tough call with these two. But here we're now going to go to some consideration we had in Chapter 5. This has a tetrasubstituted alkene. This one only has a disubstituted alkene. And each of them has another disubstituted alkene, but the degree of substitution is the same for the double bond that I've designated as isolated. All right. So this is how we're going to rank it. Number 1 is the completely conjugated system in the upper right. Number 2 is the one that's conjugated once and has the tetrasubstituted alkene group. Number 3 is the one that's singly conjugated also, but only has disubstituted alkene groups. Number 4 is the isolated. It's the one with isolated double bonds. And number 5 is the one with accumulating. So it's fully conjugated, partially conjugated, but a better alkene arrangement, partially conjugated, isolated, and accumulating. Okay? All right. Let's look at some structural issues of conjugated dienes and cumulines. What is making a conjugated diene more stable? And it has to do with the fact that when you have these 4 consecutive sp2 carbons and you draw them planar, our p orbitals can overlap all throughout these 4 carbons. When we do this, we actually have some degree of double bond character right there. Not as much as on the ends, but there is a higher degree of double bond character there. Okay? Or a small degree, actually a very small degree of pi bond character there as well. It's only when the system is perfectly flat that we can have this type of conjugation. Okay, and there are 2 ways, 2 conformations that will have this perfect conjugation over all 4 systems. We have the S-trans conformation, where it's kind of in a more extended fashion, and we have this S-cis conformation. Let's just draw them as, actually they're a little easier to see as bond line crap. Sorry about the email thing. I forgot to turn it off before making the video. All right. Okay, so it's only when it's in this perfectly flat conformation can we have this orbital overlap over all 4 carbons. Okay? All right, and it turns out that these are the 2 major conformations. Equilibrium favors the S-trans conformation due to the steric destabilization, to the fact that these inside hydrogens in the S-cis conformation are getting a little bit too close to each other. So this is sterically destabilized. Okay, and you can see it a little bit better over here. All right, so what happens if we rotate it 90 degrees? I'll try and draw a picture, but this picture isn't really all that good. Okay. What you see here is that there's no overlap. So there's only overlap when the system is completely planar. Okay, let's look at a structural issue with our other unique type of diene arrangement. That's the cumulene system here. All right, so and we've discussed this. I guess you probably consider it back in chapter 2. These were the ones you probably call the trick questions on the quiz. Okay, all right. So the sp hybridization means that there are 2 p orbitals at this carbon that are at 90-degree angles, right? P orbitals exist along the Cartesian axis. So of course the p orbitals are at 90-degree angles to each other. All right, so this sp hybridization right here means we've got 2 p orbitals that we left out of the hybridization scheme. Okay, one of them is going to do the pi bond to one side, one of them is going to do the pi bond to the other side. And we get this arrangement here where the or the sigma bonds on one end of the cumulene system are at 90 degrees to the sigma bonds at the other. If we have different substituents on each of those carbons, we actually have a chiral molecule. There's no plane of symmetry in this molecule, and if you try to superimpose it on its mirror image, it won't do that. So this is kind of a unique way to make a chiral molecule. Not the most common, because this really is not all that common of a structure. But yes, it can also serve as a source of chirality. So a carbon with 4 different things attached to it is not really the only thing we can have that gives rise, or that qualifies as a chiral center. Okay, I believe this is where I'm going to end this video, because we're going to now talk about reactions, right? Okay? All right, so let's end this one right here.